76 days remain before everything might change. While most of the world celebrated the new year, raising glasses to close out what some called the Year of the Comet, three-eyed Atlas was already slicing through the void, racing toward Jupiter at nearly 40 kilometers per second with no sign of deceleration. March 16, 2026, has quietly become a countdown embedded in calendars across observatories and space agencies. Three details frame this story, and none of them fit the narrative we've been told about natural objects passing through our solar system. First, magnetic dust-like particles roughly 10 microns in diameter are falling through Earth's atmosphere, not occasionally but persistently. These particles are too large, too uniform in size, and too consistent in their arrival pattern to be random debris from a fragmenting comet tail. Natural fragmentation creates chaos, a spectrum of sizes, irregular shapes, and unpredictable distribution. What we're detecting instead resembles precision, as though each particle was manufactured to a specific specification. Second, the object glows blue. Not the warm orange-red of a body heated by proximity to the sun, but a cold, eerie blue luminescence that intensifies even as Atlas moves away from our star. This contradicts what we previously thought about how objects behave in deep space. Cooling curves are predictable, governed by thermodynamics that don't bend for mystery. Yet, here we are, watching something that defies the expected fade as if it carries its own light source independent of the sun. Third, its trajectory already exceeds escape velocity from the solar system. It's moving fast enough to leave and never return. And yet, it doesn't. Instead, it bends inward, altering its path with surgical precision toward Jupiter, as though the largest planet in our neighborhood isn't an obstacle to avoid, but a destination to reach. Rocks don't do this. What we're watching behaves like something with intent. Let's look closer at the data. The dust cloud Atlas left in its wake doesn't behave like the chaotic spray of a comet shedding mass. It behaves like a controlled release. When scientists measured the optical depth of this cloud, the value returned as exactly 1. Not 0.8, not 1.3, but 1. A precise mathematical threshold that represents perfect concealment without complete disappearance. Nature doesn't do exact. Nature does approximate variation and noise. This is a signal. Spectroscopic analysis adds another layer. The composition is almost pure nickel with effectively no iron. Here is the crucial detail. Nature doesn't produce metallic nickel in isolation. Nickel-iron alloys? Yes. Meteorites carry both fused together in predictable ratios, but pure nickel, refined nickel, is a signature of processing, of extraction, of technology. It's what you'd expect from a manufactured component, not a rock that wandered in from interstellar space. Then there's the rotation. Atlas spins with a period of exactly 7.74 hours. No wobble, no drift, no precession. This is the rotation profile of a stabilized object, a gyroscope, something designed to maintain orientation. Atlas rotates like a satellite in controlled flight, maintaining attitude control for instruments that need to point in specific directions. So, what does this actually mean? If we strip away the caution and diplomatic language, we're left staring at an object that behaves less like a visitor from the Oort cloud and more like a machine. A machine heading toward Jupiter, not by accident, but by design. And Jupiter isn't just any planet. It's a dynamo, a generator of magnetic fields so intense they can fry unshielded electronics within minutes. March the 16th marks Periyove, the closest approach to Jupiter, the moment when Atlas will thread through the giant planet's magnetosphere at optimal range for energy transfer or signal relay. Miss this window and the alignment dies. This is a one-time event and the clock is ticking, but the story doesn't stay out there in the dark. It's already touching Earth. Silver noctilucent clouds have been reported drifting far beyond their usual polar boundaries. Satellite constellations have logged intermittent interference. Radio telescopes pick up flickers of static at frequencies that don't align with terrestrial broadcasts. Then there's the James Webb Space Telescope, floating at Lagrange point L2. Webb was designed to operate for a decade without significant maintenance, yet suddenly maintenance has been scheduled for early 2026. Launch manifests quietly list new payloads bound for L2, instruments whose specifications aren't publicly detailed. It's as though someone already knows something is out there, something worth watching with equipment that wasn't originally part of the plan. This isn't the first time. Oumuamua passed through in 2017, accelerating as it left. Borisov followed in 2019, but now the intervals are shrinking. A rhythm is emerging, like a pattern of check-ins, like someone running a survey, collecting data not to make contact, but to record, to catalog, to observe. Maybe we were never the explorers, maybe we were always the observed, and maybe 3I Atlas, silent and deliberate and accelerating toward the largest target in the solar system, isn't here to speak to us. Maybe it's here to report. 76 days remain. Whatever happens at Jupiter will decide whether we misunderstood everything. As we established, the dust falling through Earth's atmosphere isn't behaving like debris, it's behaving like a payload. To understand why this matters, we need to zoom in on what these particles actually are. When atmospheric sampling stations began detecting these 10-micron particles, the first assumption was contamination, but the magnetic signature didn't match. These particles align with magnetic fields in ways that suggest embedded structure. They're engineered grains that survive re-entry heating without disintegrating. 10 microns is not arbitrary. It's the threshold size where atmospheric drag becomes significant but not catastrophic, where a particle can slow down enough to settle gently rather than burn up. The composition adds weight to this: pure nickel with no iron contamination. Spectroscopy doesn't lie. This contradicts what we previously thought about interstellar objects, which should carry messy chemical fingerprints. Here is the crucial detail: the isotopic ratio. The nickel in these particles doesn't quite match solar system values. It's shifted in a way that suggests isotopic enrichment, a process that requires technology. Nature doesn't enrich isotopes, civilizations do. Achieving an optical depth of exactly 1 requires control over particle size, distribution density, and spatial arrangement. This is the signature of a controlled release mechanism. Building on this, we can model how these particles spread. The Atlas particle cloud expands spherically and symmetrically, requiring an internal mechanism to impart momentum uniformly. The particles began appearing roughly 6 weeks after Atlas passed perihelion, yet Atlas showed no visible coma or signs of volatiles boiling off. The release was timed. If 3I Atlas is a probe, then the dust isn't waste, it's functional. Maybe each grain is a microsensor designed to sample Earth's atmosphere and transmit findings back to the parent craft. The dust falling through our skies connects directly to what's about to happen at Jupiter. If these particles are part of a coordinated mission, then their deployment timing relative to the Jupiter encounter isn't a coincidence. Step 1. Seed the third planet. Step 2. Rendezvous with the giant. Step 3. Transmit or amplify whatever comes next on March 16th. Now we must confront the movement itself. Atlas is accelerating in a way that increased as it moved past perihelion and continued toward Jupiter. Normally, as a comet retreats from the Sun, heating decreases and acceleration fades. Atlas does the opposite. Its acceleration peaked where solar heating should be minimal. Spectroscopy hasn't detected the supervolatiles necessary to explain this. Here is the crucial detail: the acceleration vector. Atlas's vector stays remarkably consistent, pointing almost exactly along its direction of travel. This is what you'd expect from a rocket engine performing a directed propulsion burn. The rotation is equally telling. Atlas spins at 7.74 hours, locked and stable. Every asteroid we've studied shows some evolution in rotation due to torques. Atlas shows none, suggesting an active stabilization system. If it's maintaining attitude control, then it has a preferred orientation for instruments or antennas. And then there's the blue glow. Thermodynamics tells us temperature depends on energy balance. Atlas violates this. Its blue luminescence intensified as it moved outbound, suggesting an internal heat source generating energy independent of solar input. Blue light is high-energy, short-wavelength emission, the kind you get from hot plasma or electrical arcs. The 7.74-hour rotation might not be spin at all, it might be a scan rate. The trajectory tells a story. Atlas executed a course correction to aim for Jupiter. Why? Because Jupiter's magnetic field is the strongest in the solar system. For a probe designed to handle those conditions, Jupiter becomes a planetary-scale amplifier. If you can couple a transmitter to those massive magnetic field lines, you've built a broadcast station with power that dwarfs onboard systems. Jupiter could serve as a relay to send a signal across interstellar distances. This isn't an isolated event. Oumuamua arrived in 2017, accelerating as it left. Borisov followed in 2019. Now Atlas in late 2025. 3 objects in 8 years with shrinking intervals suggests a schedule. Trajectory clustering, the direction these objects approached from, shows they don't scatter randomly, they cluster within a narrow cone. This suggests they originate from a common source or a coordinated mission architecture. Oumuamua might have been the scout, Borisov the follow-up, and Atlas the reporter tasked with summarizing findings. Interstellar communication isn't instantaneous. If Atlas transmits in March 2026, that report would reach its target years later. The nearest star system, Alpha Centauri, is 4 light-years away. The trajectory clustering points slightly away from the nearest stars, perhaps toward a grid of relay stations. This connects to the Webb telescope maintenance. Positioning additional surveillance assets at L2 makes sense if you want a million-mile buffer to watch the Jupiter encounter. The signs are already here on Earth. Noctilucent clouds are nucleating on Atlas's 10-micron particles, creating visible displays far beyond their normal range. Observers in the American Midwest and Northern Africa have reported sightings. Sampling confirms nickel-rich grains embedded in these ice crystals. This is proof the deployment worked. GPS constellations have logged intermittent anomalies where receivers lose lock, correlating with regions where these clouds are most frequent. Communication satellites have briefly gone offline. If the interference is deliberate, we're being probed in subtle, deniable ways. Perigove occurs on March 16th at approximately 14:33 UTC. Atlas will pass within 600,000 kilometers of Jupiter's cloud tops. Radiation levels there would sterilize any biological organism, yet Atlas is targeting this environment. It's built to handle conditions that would destroy anything we've ever built. The most likely scenario is that Atlas couples with the magnetosphere and initiates a high-power transmission. The energy could be extracted directly from the planetary dynamo, turning Jupiter into a beacon visible across light-years. March 16th is the optimal moment when Jupiter, Earth, and potentially target star systems align to maximize efficiency. Atlas has been accelerating toward this date with surgical precision. If the particles are designed to activate in response to the Jupiter transmission, the anomalies on Earth might intensify. We might be bystanders watching a conversation unfold in our own backyard, unable to participate. Maybe we were never the explorers. We were the data,